Good evening and welcome to this, the fifth and penultimate evening tech talk by CED in the current year's season. It's great to have you along, and thank you for everybody who's there and who have supported us through this series. Just to give you a heads up, the next talk will be on the 3rd of June and will be to do with well design and construction, and will be presented by Malcolm Anderson. But back to tonight, we are delighted that David Bookham, who is a chartered engineer with 50 years experience in electronic and electrical design, is returning to talk to us tonight about solar power in the developing world. Okay, David, thank you very much, and over to you.
Thanks, Angus. So we've written this presentation for CED members and supporters, for village energy committees and for funding agencies. The context of the talk is that it's intended to address sites that have no grid connection, and we're going to be assuming that it needs to support at least 10 kilowatts of load, and that those loads are AC and that storage batteries are installed. There's numerous books available addressing solar PV, and the three that we'll be referencing are the IET Electrical Safety Standard and the Codes of Practice for Solar PV and Battery Installations. Now, whilst these don't cover the calculations determining the number of panels or the size of inverters, they do provide a lot of information on the safety aspects of the installation. Note that whilst the second reference is for grid-connected systems, much of the information also applies to off-grid systems as well. So today's presentation is going to be in 4 parts, covering basic electrical theory, then the survey of the power and energy that's currently being used or projected to be used. And then we'll undertake some the calculations and determine what equipment needs to be specified. The talk is intended to explain the initial conceptual design, and any actual design and installation must be undertaken by a qualified engineer. Firstly, a little quiz. On the left are 2 LED light bulbs. Each of these is 8 watts and they're on for 12 hours a day. On the right you see a 700 watt rice cooker which is being used for 15 minutes. So the question are: A, which of these 2 applications consume more energy? B, which determines the size of the solar PV array? C, which determines the power rating of the PV inverter? And D, which determines the size of the storage batteries? Before answering the previous questions, we're going to take a look at a few electrical basics, the sort of things you did at school and physics lessons. So we learned that Ohm's law defines resistance as voltage divided by current, and this means that the voltage drop across a cable is the resistance multiplied by the current. Likewise, the current that passes through that wire is the voltage divided by the resistance. The electrical voltage is available in either AC or DC, where AC is alternating current is normally referred to as the RMS voltage. This is the value of the highest useful power, but it has a peak-to-peak voltage which is significantly higher, and this will affect the safety aspects of the design. Coming back to power again, and from Ohm's law, power is voltage multiplied by current, or voltage squared divided by the resistance, or the current squared multiplied by the resistance. If we're dealing with AC signals, then we have a power which is related to the current multiplied by the voltage, but this is only applicable where the 2 are precisely in phase with each other. If we're running with an inductive or capacitive load, then there'll be a phase shift between the current and the voltage. This determines the power factor. So we get over the apparent power measured in kVA, whereas the power factor is the kilowatt power divided by the apparent power. Typically power factors are in the order of about 0.9 to 1. When we're dealing with higher powers, we use 3 phases, where each of these phases is 120 degrees apart, and it's important that we have good phase and power balance on all 3 lines. Another basic value is energy, and this is related to the duration of the power being consumed. So a joule is 1 watt of power being consumed for 1 second. So a kilowatt hour is 1 kilowatt running for 1 hour. When we're considering solar PV systems, there are several different configurations available to us, and an off-grid system will comprise of several solar panels connected in series and feeding DC to AC inverters. These are called string inverters or solar inverters. They in turn generate the AC supply to the load. If we need battery backup, then we need to convert this AC supply back to DC again to charge the batteries, and then convert it back to AC again when it's required. We might also incorporate a diesel generator should the solar system fail altogether. Another type of inverter is the microinverter. These are small inverters, about the size of a paperback book, and typically will have one on every panel, or maybe one over every 4 panels. Microinverters are distributed across the entire array, rather than being in a single remote location. Another type of inverter, sometimes referred to as a power bank, combines multiple functions into a single enclosure. The unit includes the AC-DC conversion, the charge controller for the batteries, the battery management system, the batteries themselves, and the DC to AC inverter. Hybrid inverters incorporate the same functionality as a string inverter, charge controller, the battery management system, and the DC to AC inverter. We also need to consider frequency and phase synchronization. Now, if we're operating on a grid-tied system, then the reference comes from the grid, or perhaps a generator in the case of an off-grid system. For an off-grid system, this reference isn't available, and we must generate it within the inverters themselves. So now let's return to the quiz and see that the lighting, which used 2 8-watt bulbs, were on for a total of 12 hours. So 16 times 12 is 192 watt hours of energy being used. The rice cooker uses 700 watts of power, but it's only on for a quarter of an hour, so equaling 175 watt hours. So what can we conclude from this? Well, obviously the item that consumes the most energy is lighting, which is 192 watt hours. But the solar array must be able to provide at least 367 watt hours of energy daily. The inverters will need to support the highest power, which is 700 watts through the cooker, and the batteries must be capable of supplying the energy for the lighting, which is 192 watt hours, throughout the 12 hours of night. So what about all the losses? There will be losses in the DC cabling from the panels to the inverter, and the AC cabling from the inverter to the load. There will also be losses within the inverter, which will vary with load and temperature. There will also be charge and discharge loss due to the batteries and the long-term degradation of both the panels and the batteries. Both of these will be dependent upon temperature. Finally, the load may change over the lifetime of the installation as more equipment is added to the system. In terms of the availability of solar energy, this will vary across the day and across the year. And additionally, we may get shading, which might change with leaf coverage on nearby trees. In terms of system reliability, we may have a panel failure, and if we're using series connected strings of panels, then these will affect the entire string. If we have an inverter failure and we're using a single converter, this can lead to a single point of failure. And if we have a battery failure, this can cause problems if we have series connected batteries. Finally, if we have switchgear failure or cabling being gnawed away by rodents, this also could cause an outage. We now need to look at the requirements of our installation. What loads are being used, what time of day are they operating, and for how long are they operating. So this is going to involve producing a spreadsheet listing every single device on site This will be quite extensive, and for the installation I was recently involved in, we had to work on that for almost 2 days, going around every single room and working out what equipment was installed and what equipment might be added later on. Since this resulted in a huge spreadsheet, I've summarised it in this table. Starting with the first row, the lighting in the accommodation block is the total power consumed by all the lights in all of the rooms. We can see that lights come on at dusk and they remain on whilst the occupants are awake. I've itemised different types of outlets simply because they could be low power loads and high power loads, and they may be on at different times of the day and for different durations. And so on for the remaining rooms: washrooms, corridor, common room and office, etc. Moving on to the next slide, we see a further breakdown of those items that are being used in the kitchen. The kitchen's interesting because not all the items are going to be consuming power all the time. So think about the cooker, which potentially consumes 6.7 kilowatts, but only whilst it's warming up. Once it arrives at the desired temperature, the thermostat trips, the heating element is switched off. Similarly, the washing machine and the laundry will exhibit the same principle. So we've used the manufacturer's energy figures rather than simply taking the power and multiplying it by the duration for this table. To give an idea of this, the washing machine consumes a peak power of 2.3 kilowatts. So if it were on for 1 hour, you can imagine it would take 2.3 kilowatt hours of energy. However, the manufacturer's data states that the energy used over a single wash cycle is just 0.8 of a kilowatt hour. So we're now in a position to analyse the power and energy usage and to optimise them both. From this chart we can see that the peak time for the power usage is between 6 PM and 10 PM, as can be deduced from our spreadsheet. So if you look at the column labelled kilowatt peak, we can see that between the hours of 6 and 10 PM the lighting in the accommodation is consuming 0.21 kilowatts, and during the same hours we are using outlets A and B, together with power in the washrooms, corridors, common room, office and kitchen. So adding all these numbers together, we end up with a number over here in light blue of 23.29 kilowatts. We can also analyse how the power is being consumed within each location, and you'll notice that the total of 13.49 kilowatts, the kitchen consumes the most, which is not really surprising when you consider it includes a cooker, kettle and washing machine, all of which incorporate heating elements. In order to analyse how much energy is being used, we could simply just multiply the power consumed by the duration. This works for lighting, computers and TV, but we can't use this simplicity when we look for the energy that's being used by devices that intermittently consume power. Take for example the oven. Again, each time it reaches the required temperature, the thermostat trips, the heating element is switched off. Whilst for the washing machine, the heating element only comes on to bring the water to the correct temperature, and thereafter it's just the motor that's consuming energy. The satellite internet router will be consuming quiescent power on receive, but this will increase each time it transmits. Incidentally, if you're interested in knowing more about how to reduce this, then take a look at my CED Tech Talk, which is entitled Communications. So now let's look at the energy, and we can see that the peak energy is being consumed again in the evening, as we'd expect, because the staff are in the common room with the air conditioning running, and prior to that they're in the kitchen cooking their dinner. The majority of the energy, however, is actually being consumed within the office, because the administrator will be sitting there and will have the air conditioning on for the full 8 hours that they're at their desk. So whilst the power is lower compared to the appliances in the kitchen, the total running time multiplied by that power means that the office is where the most energy is being consumed. So how could we optimise this? One solution is to reduce the total load, and we can do this by using energy efficient light bulbs and ensuring that the rooms are all that are air conditioned have adequate sealing around the doors and windows. If we're using a hob, then an induction hob is more efficient than a traditional electric ring, And if we're using an oven that is fan assisted, and a fan assisted oven consumes less energy than one without a fan. We can also change the timing at which the loads are occurring. So for example, we could have motion sensors on the lights, so they're only coming on when necessary. And any high power loads, for example the water pump for the groundwater extraction, only operates when we have excess power available, perhaps midday. To summarise, the peak power is 23 kilowatts. The peak current occurs in the evening as the air conditioning and cooker are used, and the peak energy is 86 kilowatt hours for the whole day. And of this, 43% of that energy is actually used in the office. Now we'll know what the loading will be. We need to figure out what size of power source we need. First thing to do is to estimate the potential solar density at the site, and then determine the tilt angle of the panels and the azimuth angle at which the panels are going to be pointing. We can then also look at the surrounding area and determine any shading and, if possible, undertake some measurements on the actual electrical load. So this presentation is actually based on an actual site which is located slightly north of the equator. The panels are mounted on the roof of the building, but the roof pitch and azimuth are not optimised. The maximum temperature recorded at that site and the radiation density was estimated using the EU PVGS software. This resulted in monthly radiation densities of between 120 and 210 watt hours per square metre from the 18 years of available records of that site. We're using the minimum values rather than the annual values because its site is off-grid and so must operate every month of the year. Obviously, the available solar power varies across the day, rising from dawn to a peak midday and then diminishing back down towards dusk again. So we're going to take a look at the solar panels, the inverters and the batteries that might be required to achieve the energy requirements at that site. As we determined earlier, the site requires 86 kilowatt hours of energy every day, which equates to 2,662 kilowatt hours per month. The available energy density is around 120 kilowatt hours per metre squared per month of solar panels, so the collection area would be around 22 square metres if they were 100% efficient, which is obviously not going to be possible. Since the panels are only 22% efficient, we actually need about 100 square metres. Assuming we're using a 615 watt panels and the collection area of each panel is around 2.56 metres squared, we divide it through and we end up with the minimum number of panels being 40, assuming no margins and no system degradation. So now we'll take a look at estimating those losses and equipment degradation. First, we'll look at the losses in the DC wiring from the panels themselves. The IET recommendation is less than 3% voltage drop within the DC cabling. This is measured at the maximum power point for the voltage and current of the PV array. We learnt earlier that Ohm's law specifies the voltage drop as current multiplied by resistance, and in this case the resistance will be the sum of the drop cables together with all the linking cables to the inverters. So it may be that we need to increase the wire size to reduce the resistance and hence minimise the voltage loss. We also saw earlier that Ohm's law says that the power is equal to the voltage squared divided by the resistance. So if we have 3% voltage drop, then there's actually going to be 6% power drop. If we're using parallel strings of panels, then we'll have a combiner box, and the cabling from the strings may be a smaller diameter than the cabling from the combiner box down into the inverter. Now we'll look at the panels themselves and we determine the maximum ambient temperature at this particular site is 32 Celsius, and the typical temperature coefficient of a panel is around minus 0.29% for every degree of change in temperature. The standard temperature for specifying a panel is 25 Celsius, so the maximum thermal loss is going to be the difference between 32 and 25 multiplied by the temperature coefficient of the panel, which gives us around 2% loss. The panels themselves will have a long-term degradation in output, and for a high-grade panel this is specified over 30 years and could be around 12.5%. Other types of losses that we may come across will be due to the pitch of the array and the azimuth orientation. So based on the actual location, we've calculated 4%. Shading isn't a problem at this particular location, because whilst there are a number of trees to the north side of the building, there's actually only one skinny palm tree on the southwest side of the building, and so we've only put in 1% for the shading caused by that tree. Contamination is more of a concern, and at this particular site it has a low pitch roof of just 10 degrees, so it's likely to retain dust, but it's situated in quite an open environment, so we're hoping that the wind together with the monsoon rains should help to reduce contamination, but as a precaution we're scheduling a regular maintenance. Moving on to the inverters. A PV string inverter typically exhibits about 97% efficiency, but this degrades with temperature and low loading. The charger controller and the battery inverter is typically around 95% efficiency, but again degrades with temperature. The IET specified that the IC voltage drop should be less than around 1% at the rated power of the system, which equates to around 2% power loss. Now if we multiply all these numbers together, we end up with a total loss of around 31%. Incidentally, those who are observant and have tried adding these numbers together will realise that this list doesn't add up to 31, and that's because we're multiplying these percentages, so in fact it's 0.94 times 0.98 times 0.96, etc., etc. Now if we take the total power loss as 31%, it means that the total number of panels increases from 40 to 58. And if we want to include an allowance for a 30-year lifetime of the system, then this increases still further to 66 panels. If the panels are 615 watts, then this gives us 66 times 615, which is approximately 40 kilowatts peak power from the array. We're now moving on to the batteries, and from earlier calculations the total energy of the site is 86 kilowatt hours per day, but from the pie charts we could see that not all this requires energy to be stored in the batteries. Since lithium batteries normally operate with an 80% depth of discharge at 25 Celsius, this means that for us to provide 86 kilowatt hours daily, a battery size is required of around 107 kilowatt hours. But the degradations of the battery over the lifetime is typically around 60% of the rated capacity after 10 years at 20 degrees centigrade, or 7 years when operating at 30 degrees centigrade. So this gives us around 179 kilowatt hour requirement. Due to the weather extremes, a 179 kilowatt hour system may have insufficient battery capacity for around 72 hours a year, when it degrades to around 280 hours after 7 years. And we can improve these numbers if we run the system at lower temperatures. We could also decide not to design for a 7 to 10 year lifetime and simply provide 107 kilowatt hour capacity. But it's generally easier to get donors to seed fund the original project rather than donate to a maintenance fund later on. Moving on to sizing of the inverters, the peak power consumption for the site is 23 kilowatts, and this occurs, as you'll see earlier, between 6 and 10 p.m. We don't want to use a single inverter that could provide a single point of failure, and so we've ended up with multiple inverters. Summarising all of this, we can see that in order to supply a peak load, we need to have at least 40 kilowatts peak capacity from the solar panels, at least 179 kilowatts of hours of battery capacity, and solar inverters totaling well in excess of 23 kilowatts. In fact, the inverters must be capable of accepting the full load from the panels without damage anyway. Because the solar system will not provide all the power 100% of the time across the year, the generator will still be required. And we've selected to use a changeover switch rather than incorporating load sharing. This is for several reasons. Firstly, when using load sharing, an external controller is required, which adds additional cost. Secondly, diesel generators generally need to operate between 70 and 80% loading to provide maximum efficiency, and certainly no less than 30%, or they'll slobber. Lack of torque and also require regular maintenance. Whilst an external load bank would avoid these issues, it would be wasteful. And thirdly, because of the high power available from the solar array, backfeed protection circuits may be required to prevent the inverters driving current backwards into the generator. In addition to calculating the major components, the project also involves determining where the equipment is going to be mounted, the routing of the cables, the selection of the isolators and the switchgear, fuses, and lightning arresters. Additionally, we'll also need to consider environmental control to reduce the battery and inverter temperatures, and of course the installation will require contracting different tradesmen as well as a qualified commissioning engineer. All of these aspects will not be discussed further in this presentation, but perhaps could be part of a future Tech Talk. Similarly, the completed system needs to be monitored and controlled, and this will involve current and voltage probes connected to the inverters and the battery management system, and then extending the capability locally using Modbus or remotely using IP or perhaps SNMP over Ethernet. Safety considerations that need to be taken into account will address high voltages, high currents, battery management, generator protection, lightning protection, and surge arresting and wind loading. Method statements needs to be written to ensure safe undertaking of routine maintenance and replacing faulty equipment. As a return on investment, obviously we're saving diesel, and very important to this particular site is the transportation, because in extreme weather conditions the site is completely cut off. But we need to offset these savings against the cost of the annual maintenance and the cost of end-of-life replacement of the batteries. We also considered how the site might be used in the future, and perhaps there might be more power being consumed. We also did consider what might happen if the grid ever should arrive at that site, and if so, whether exporting power back to the grid might even be feasible. Finally, thank you all very much for listening to this presentation. I'd like to thank Graham Miller for reviewing it and providing some constructive criticism. Thank you all,